Alrighty, so we are going to go through some solving. We're going to do some problems that don't require logarithms, some that do. We're going to do real world problems and just kind of some generic ones that include a log in the problem, and we'll look at all of those. These you might have seen in Algebra 1. We can use logarithms for it, but because we might see that 10, 1/10, and 100 have common bases, they both can be expressed as powers of 10. Like 100 could be 10 squared, and 1/10 can be 10 to the negative first. That allows us to have the same base, and once we kind of clear these parentheses, we get something that looks like this. So 10 to the 2x, 10 to the negative x plus 3. What's great is if the bases are the same, they essentially cancel out. If we want to solve this problem, we say, well, what would make the exponents the same? Well, let's find the x value of when they are equal. So we'll add x. We get 3x equals 3. And x equals 1. I don't know why I boxed that, but I did. So x equals 1, obviously, here. Sometimes you might have to change both bases, and you have to look and like, all right, what numbers do these have a common base of? I can't really, I know that 125 is divisible by 25, but the exponents kind of stop you because of order of operations here. So our goal will be to replace them with things that are worth the same. So 5 squared and 5 to the third. But now we can do this so that they have the same bases. We can distribute their exponents. So 5 to the 4x equals 5 to the 3x plus 6. And essentially, again, lack of a better term, we're going to cancel out the exponents, or the bases here, I'm sorry. And that gives us something that looks like this, and we can solve x equals 6. And this time I'll box the correct answer. Well, this one we have an issue. There's no power of 2 that's going to get me 7. I know that's going to be like maybe a little less than 3, because 2 to the third is 8, right? So that's kind of my expected answer. What's great is I could do something like this. I could say log base 2 of 7 equals x. That gets my exponent by the same. But I can't put log base 2 in my calculator. So what I'm going to do is I'm going to use the change of base formula. You might need to look that back up. And say log of 7 over log of 2 equals x. Remember, these are both log base 10 here. And I can put that in my calculator. I could have also done this at the ln. But I'm going to use... I just use log because, well, I don't know, felt like it. And so log of 2. And I get a number. I'm going to round it. Let's round to the nearest hundredth, 2.81. So x equals 2.81. Like I said, I was expecting something a little less than 3, which is a good idea to always kind of check. So I'm going to check this time to the 2.81. And that was the question I answered. And so obviously I rounded up, so that kind of had an issue there. But close enough there. All right. This is going to look really intimidating. I'm going to break down this equation, but ultimately we're going to substitute numbers in, and we're going to try and isolate down to this e. And so I'll explain how that works. So the whole concept's when you put something in room temperature or into a submerged around a significant temperature. And I'm going to go ahead and draw a little kind of concept of the graph here, is that you have something and it can either cool or it could heat up, right? Either way it works. But it's going to be basically a log graph. You know, we have our vertical asymptote here, or an exponential graph, sorry. And you approach a temperature. I like to cook sous vide, which means you submerge your food into a heated bath of water, and there's like a little circulator here, and it gets it to the perfect temperature, right? You get right to that temperature. And that's what's happening here. So I'm going to break this equation down. This equation sometimes is written differently, but let's kind of look at a few things here. I'm going to say T of R, that's going to be our room temperature. So we're going to say T of R is 70. T sub 0 is the initial temperature of our whatever we're doing. So we're going to say 212. So like 0 is often used as a subnumber for initial. This cooling rate is given to us. Normally what you'd do if you were actually doing a real problem like this, you would solve for this by finding two data points of like measuring the temperature at two different times to kind of approximate for that. This is going to be our final temperature. So this is just going to be straight up our T is going to be our final. Oftentimes, so T is going to be our final. So we're going to say T is 100. So I wrote a lot here. We have our R just given to us. Remember, E is not a variable. All right, so let's plug everything in. So I'm going to have 100 equals 70. Oh, no, not 70, sorry, 212 minus 70 to the E to the negative 0.046 T. We don't know the time. That's what we're looking for. Plus 70. There's some stuff that we can simplify here. Again, I'm going to bust out my calculator. I'm going to be ready for that. So I got 142. So I have 100 equals 142 e to the negative 0.046 t plus 70. I like actually, there's sometimes this t of r is in the front of the equation, but I actually kind of like it on this side because it makes it clear that I'm just going to go ahead and subtract that. So I'm just solving this like a regular equation. Oops, let's get this 2. Make sure right numbers. I keep missing them. There we go. A lot of writing in this one. So I'm trying to get this e down to itself. So again, this is a coefficient. I'm using order of operations. I'm going to leave this as this fraction too. So we're going to get to the main step. What I've done so far is I really was trying to get e to the negative whatever, 0.046 t. I was trying to get this by itself. What we know is that a logarithm, one way to think about it is if we want to get rid of this exponent variable to make sure that it's isolated, we're going to go ahead and take the natural log of both sides. And the reason I'm using ln, if you remember, ln is log base e, right? And one fact that happens is that if I had ln of e to some exponent, that just equals x. These invert each other. But I'd have to do it to both sides of the equation here. There is another way you could also think of this as rewriting into logarithm, but I find that this is what people like the best for solving problems. So on this side, that cancels out. And what we get is ln of 30 over 142 equals negative 0.046 t. And this is something we're going to put in a calculator. I'm just going to keep that like that for now so that I can put my last part in the calculator all together. So I'm actually going to end up, so I don't have a rounding issue, I'm going to put this all in the calculator. Ultimately, you're just going to use some parentheses to make sure that everything stays cool. So I'm going to close my parentheses there, divided by that negative 0.046. So 33 point, let's see, let's call it 0.8. 33.8 seconds. Or is this in minutes? Let's find out. T equals 33.8. So actually, you know what, when I look back at this problem, it did not tell me what the units for this is. So oftentimes, if you're solving for it, whatever units you use to solve for this R, we give it to you. In this case, we don't know the units. Some unit of time, I guess. All right. There is a pretty obvious property here. It kind of is almost similar to the property I used down here. If the bases are the same, they cancel out. And that's ultimately what this is saying. All right. So let's go to the second page. This is pretty simple. Hey, what would make these the same? Well, if the insides were the same. So we just say 4x minus 7 equals x plus 5. I mean, that seems pretty intuitive. There's no curveballs. It sounded like I was going to tell you a curveball there. I'm also going to add my 7 to each side here. Make this a little easier. I'll rewrite my problem up here. 3x equals 12. Therefore, x equals 4. But this one doesn't have logs on each side. And there's this stuff on the inside. Now this doesn't have a number by itself, right? Like log 2 is not a thing I can undo. But I can reformat this. I can rewrite just in the same way that we use like log base b of a equals x is the same as b to the x equals a. What's cool is that if I do that, my variables will be all isolated. So I'm going to call this 2 to the third equals 5x minus 17. I'll show you another way on this problem, but that's the cleanest way, I think, is to go from here to here. So 2 to the third is 8, so we have 5x minus 17. We're going to add 17, and then that gives us 25 equals 5x, and so therefore x equals 5. The alternative way you could think of this, and I probably would not recommend, I think just reformatting is a great way to think about it. We'll get to the same step, but the concept is exponentiating. That's a fun word to say. And so I'm going to raise both to the 2 power, or 2 is going to be my base, and then one of the properties was 2 to the log base 2 would just be cancel out, and we'd be left with that. And we'd get 5x minus 17 equals 2 to the third, which is what I had over there. If you like having, like not reformatting, but having an operation to do, well, this operation is called exponentiating, okay? Exponentiating. And I don't know if I actually spelled that right, but it's fun to say. We're going to do a similar thing on this one, but first we need to get the logs down into 1. So this is the product property. I'm looking, I see a plus here. That means I'm going to multiply what I have as my insides. So I'm going to have log of 2x squared minus 10x, because I'm going to distribute, I'm multiplying 2x times x minus 5 equals 2. I can think of this as exponentiating if I want, or I can rewrite it regardless of what you do. Remember, this is a log base 10, so I'm going to say 10 squared equals 2x squared minus 10x. 10 squared is 100. Now this is a quadratic. We're getting to the point in algebra where we just need to be ready for any potential type of algebra question. Why am I subtracting this 100? So I can get it equal to 0 on one side and factor. Will you always have to factor? No. It depends, and you just got to be on your toes for the different possibilities that may come up. Now I'm hoping this will factor. If it doesn't, man, got a lot of work cut out for us probably. All right, so we're really just factoring this puppy right here, the inside of that. I'm going to do a little diamond problem and put negative 50 on top. And maybe you factor a little different. That's totally cool. This is a coefficient of 1, so I can kind of take my shortcut here. So I believe negative 10 and positive 5. Those, everything checks out here. So I get 0 equals 2 times x minus 10, x plus 5. X is going to equal 10, and x is going to equal negative 5. That 2 doesn't really affect the problem. And ta-da, we did it. Now we might want to check these answers because, actually, you know what? I'm sorry, we're not going to get any, we'll be fine on these. I was going to say if we had an x over here, we might be careful for a extraneous solution. But in this case, we should be fine because the result, actually, let's double check that. I'm rambling a little bit, so let's find out. The concept being that if we had, and I think there's going to be an issue, particularly with this one, okay? The idea is that if I had log of log base 10 of 10 minus 5, okay, here's the question, and we can even see this, log of negative 5. This means 10 to some power is negative 5. Exponents can't really do that, right? So in this case, this particular part doesn't have any value associated, and we can even see that. Luckily, this is log base 10, so you're going to find if I put log of a negative number, I get a domain error. And you know what's going to happen is actually on this other part over here, I'm also going to get a domain error. When I put in this one, -5 here, I'm going to get log of 2 times -5. So I'd get log of -10. And that's not going to work because, again, if there's a negative in here, that's not going to work for us because these are the result of an exponent. There is no power that changes. Unless this base was a negative, there is nothing that's going to make this negative because of the exponent. And remember, these are the results, and the exponent's what comes out. So in this case, there's nothing that can make a negative, so it's a domain error. Rambled a little on that last part. Check your answers is always a smart idea. If we were to go back, this 5 should be fine here. That one looks good because if I plug 5, I get 25 minus 17. 2 to the third is 8, so that one checks out. This one should be fine too. All right. So there you go. Try these practice problems, and we'll hit it up later.